Section 4.4 is about a normal distribution, or in other words, it is a special kind of numerical data that shows up, then it is unimodal, it is symmetric, and it is bell-shaped. Many populations can be reasonably approximated by a normal curve, and a lot of times a normal curve, we're going to have a numeric variable, and it's going to be continuous. So pretty much anything that you can measure on a continuous numerical distribution is going to give us this possibility to have this sort of shape, unimodal, bell shape. This happens a lot of times anytime we have a general variation in either direction, things like body temperature or height, etc. Now, when you are dealing with this normal curve, the mean, median, and mode are all about the same. It is symmetric, so we primarily use mean to discuss our typical value measure of center. Sometimes you'll have things that are kind of bell-shaped, like this stem plot right here, and when I look at this, it does seem to be unimodal. It seems to be approximately symmetric, and just have to have that drifting off to both sides bell shape. What you want to be really careful of is when you talk about one of these, you never want to say it's a normal distribution. You want to say it is approximately normal. If something is normal, it has a very, very specific set of rules that govern that particular curve. There's actually even a mathematical equation to graph that particular curve. So here's what we know about a normal distribution. In a normal distribution, perfectly normal, not approximately normal, we have a symmetric curve and the mean is in the middle. Okay, so I've got my mean in the middle. All right, there's my mean. And standard deviation behaves in a very interesting way. If you count out one standard deviation of distance on either side of the mean, you will have trapped 68% of the data. So, for example, I know that if my mean was 10 and my standard deviation was 2, that I know that 68% of my values would be between 8 and 12. So I go up by 10, I go up by 2, I go down by 2, and I would trap those in there. Also, 95% of the data is within 2 standard deviations of the mean. So if you start at the mean and you count up 1 standard deviation and up 2 standard deviations, and then do the same thing on the other side, that particular interval of values will have 95% of the curve. And then finally, if you go up 3 standard deviations, you end up trapping 99.7. Now, there's going to be some questions on your homework that are going to ask you about some of these little intervals, so just note that this is in your notes packet. Okay, so 68%, 95, 99.7. And what we're basically saying is that as you move away from the center, there's less and less values. A lot of times we would say, you know, this is our bell curve. Most of the people are in the center, and then you have fewer and fewer as it drifts out to both sides. Okay. When you were talking about normal distributions, we use a certain notation that looks something like this. This is read, X follows a normal distribution with a mean of mu and a standard deviation of sigma. Also, we tend to put inequalities in terms of a statement like this. And this is actually going to say the probability that X is between A and B, or maybe the proportion of values that are between A and B. And you want to be careful about whether or not a problem asks you for what percent or what proportion versus a how many. Remember that how many is a counting number, like 5 or 47 or 52. What percent or proportion, that's a number between 0 and 1. All right, so over here to the side, I have a survey of 1,000 gas stations found that the price charged per gallon of a regular gas can be closely approximated by a normal distribution with a mean of $1.90 and a standard deviation of 20 cents. All right, how many of the stations charge? And there's various values here. So because I know it's normally distributed, I would start off by sketching this curve. And I'm going to label this as normal. So I'm going to put an N, a capital N up here. And I'm going to put the mean, $1.90, and the standard deviation, 20 cents, up there as well. And I'm also going to label this. This is an x-axis here. I'm going to label this with my variable, which in this case is the price. All right, there's my price. Now, when I go to deal with this curve, what I want to do is I want to put the mean in the middle. So I know that this is $1.90. The next thing I'm going to do is I'm going to try to count out by standard deviation. So there's $1.90 in the middle, and I'm going to go up 20 cents. So one standard deviation up gives me $2.10. Another standard deviation up gives me $2.30. And then finally here at the top, I would have $2.50. Okay. And then I could count out in the other direction as well. So $1.90 minus 20 cents is $1.70. And minus 20 cents gives me $1.50. And minus 20 cents gives me $1.30. All right, so if I wanted to answer this question, between $1.50 and $2.30, how many of these 1,000 gas stations are somewhere between $1.50 and $2.30? So here I see $1.50, here's $1.50, and here's $2.30. Now, since those are boundaries, I can start at my mean and I can say, okay, I'm going to go up 2 standard deviations on the left, or sorry, on the right, and then 2 standard deviations on the right. So my 68, 95, 99.7, this rule that tells me that if I'm within 2 standard deviations, within 1 standard deviation is 68, 2 standard deviations is 95, and 3 standard deviations is 99.7. So my $1.50 to $2.30, that's within 2 standard deviations. That would be 95% of those values. And since it's 1,000 gas stations, then I'm talking about 950 of those gas stations would be my answer. The next question says, what about less than $2.10? Okay, so what number of gas stations in this situation would be less than $2.10? So here's $2, and let's try and get my pen working here. Here's $2.10 right here. And less than means I'd want all of this area over to the left. Like, what is that percentage? So what do I know? Well, I know this is a normal distribution, and I know that it is symmetrical. And since it's symmetrical, that means if you fold it in half, you're going to get 50% to the left of center. So I know from here to here, that is 50% of the curve. The other thing I know is that there's 68% within 1 standard deviation. So if you split that into 2 pieces, there's 34% on the right and 34% on the left. So if I've got 50% from the center to the left, an additional 34% over to the right to that boundary, that tells me I have 84%, or out of 1,000, that would be 840 stations. Okay. Next, it says, what is the probability, or sorry, how many of those stations have more than $2.30 for gas? So here's $2.30, it's right here, and I want more, that would be this direction. All right, so that $2.30, remember that that was within 2 standard deviations on the right. So I know between $1.50 and $2.30, there are 95%, which means on the outside, if there's 95% in between those values, if that's 95%, then on the outside, I would have 5%. And so since it's split evenly because it's symmetric, I would have 2.5% on the left and 2.5% on the right. So there must be 2.5% of the curve from 230 up to infinity up here. So 2.5%. And again, out of those 1,000 gas stations, we're talking about 25 stations. All right, so I can solve problems about how likely something is, how many, based on a normal distribution is very predictable probabilities based off of that empirical rule. All right, so the next is a vegetable distributor knows that during the month of August, the weights of tomatoes were normally distributed with a mean of 0.61 pounds and a standard deviation of 0.15. So I'm going to come over here, I'm going to say normal. It has a mean of 0.61. It has a standard deviation of 0.15, okay, and the unit here is pounds. Okay, so what percent of the tomatoes weighed less than 0.76 pounds? Oh, I don't know. So let's go over here. I'm just going to say 0.61, and I'm going to go up by 0.15. So 1 standard deviation up gives me 0.76, another one gives me 0.91, another one gives me 1.06. And in the other direction, let's see, what do we have in the other direction? I'm going to subtract 0.15. That's going to give me 0.46 of a pound. Minus 0.15 gives me 0.31 of a pound. And minus 0.15 gives me 0.16. All right, so I see that 0.76 is on this boundary. What percentage of the tomatoes weighed less than 0.76 pounds? So again, this is similar to the one we did in the previous. There are 50% there, and then another 34% from that 68% cut into two pieces. So we're talking about 84%. In a shipment of 6,000 tomatoes, how many tomatoes can be expected to weigh more than 0.31? All right, here's 0.31. Okay, 0.31. More than 0.31 means I want all the way over there. So I'm going to see how far that actually is. So from the center, it's 1, 2 standard deviations to the left. And if I count out 1, 2 standard deviations to the right, that would take me to 0.91. So basically, I know this bit right here is 2 standard deviations. That's 95% of the data. So I just need to figure out what this little bit on this side is. So in order for this to add up to 100, there's got to be 2.5% over here and 2.5% over there. That's going to be put together. I'm going to get 97.5%. All right, and then it says the shipment is 6,000. So in order to figure out that total, I'm going to take 0.975 times 6,000, and I end up with 5,850 tomatoes. All right, in a shipment of 4,500 tomatoes, how many are between 0.31 and 0.91? 0.31 and 0.91. Oh, we just answered that question. Okay, so if I look again, 0.31 is here, 0.91 is here. That's 1, 2 standard deviations and 1, 2 standard deviations. So I know that's 95% according to the empirical rule, and 95% of 4,500 tomatoes gives me 5,700 tomatoes. So I can use standard deviation to find useful things about the proportion. Because it's so predictable in these percentages, it can help me out. The other thing I could say is, let's say I didn't know what the standard deviation was up there, but I knew that if I knew something like I said, oh, okay, well, I know 68% of my values are from 0.46 to 0.76. Well, I know that means that 68% of my values are within 1 standard deviation. So that means there's, my mean in the middle, and I've got 0.46 here, and I've got 0.76 here, and I know I've got a standard deviation here and a standard deviation here. I can actually figure out what that is. Okay, so I look at this and I see, okay, there's a difference of 30, and that's got to break itself up into 2 equal pieces to go out in each direction. There's my standard deviation of 15. Okay, I could do the same thing if it was 95%. I'd find the overall distance, and I know that's within 2 standard deviations on either side, so I could break it into 4 pieces. And I could estimate that standard deviation. So when we are talking about a standard normal distribution, something that does come up is something called a standardized score, or a z-score. So here we have the recent scores on an SAT are a bell-shaped distribution with a mean, I'm going to go ahead and label that, of 1,100 and a standard deviation of 20. And I made a little bit of a mistake here in my not leaving room for a comma. All right. So 1,100 is the mean, and 200 is the standard deviation. And this is score. All right, so if I wanted to estimate the percentage of scores greater than 1,300, I'd first start off by checking, okay, 1,100, I'm going to go up by 200 plus 200, there's my 1,300. I could go up, that's 1,500 and 1,700. On the other side, I could do minus 200, that gives me 900 and 700 and 500. All right, so estimate the percentage of scores greater than 1,300. I want from 1,300 up. So I know from our previous examples that there's 50% on the side. So there's 50% on the left side here from 500 up to 1,000. And another 34% because you've got 34% on either side. Okay, 34% here, making that 68. So I know there's 84%. So if I take 100 minus 84, if there's 84% on the left, I know there's got to be 16% on the right. So the percentage of scores greater than 1300 is definitely going to be 16%. Okay. The next question says, what is the percentage of scores, or estimate the percentage of scores that are greater than 750? All right, now here I'm running into a bit of a problem because 750 is somewhere in here, and I want to be able to calculate that greater than 750, but that boundary is not one of my empirical rule values. I can't do that. So I can't use the empirical rule. So right now, if it's not one of these exact number of standard deviations, then I am incapable of using the empirical rule to estimate this. Now, I could guess. I know it's going to be bigger than 84%, and it's going to be smaller than like 97.5, but I don't know between there what it's going to be. If it's not one of my boundaries, I'm kind of stuck. All right, so we're going to solve that problem in a minute, but for right now, we're going to take a detour through something called a z-score. So one thing that we can do to help ourselves out is to calculate something called a z-score. A z-score is literally the number of standard deviations between your value and the mean of your distribution. Okay, so the idea is that the z-score tells you how far away from your average your score is. The bigger your z-score is, the more unusual your value is, the more extreme your value is. So if something has a z-score of 1, that's with 1 standard deviation above the mean. That's not very unusual. If something has a z-score of 7, we're like, wow, that is really big. Okay, so how many standard deviations between that value and the mean? So a z-score of 0 would actually be the mean, and then 1 standard deviation up, 2 standard deviations up, 3 standard deviations up. Okay, to go the other direction, we would subtract -1, -2, and -3. All right, so the z-score is the number of standard deviations that you have above or below your mean. Now, the formula for a z-score is to take the actual difference between your number and the mean and to divide by the standard deviation. That's going to give you the number of z-scores, the number of standard deviations between your value and the data. Okay? All right, so I'm going to go back here. It's the same problem again, but this time it says the scores of a recent SAT are a bell-shaped distribution with a mean of 1100 and a standard deviation. Calculate the z-score for a test score of 1300. Now, if you remember, 1300 was right here up at the top of the page. Okay, 1100 plus 200, 1300. Okay, I'm going to go ahead and label this. I can tell that using z-scores, this ought to be a z-score of 1. Okay, a z-score of 1 because 1300 was 1 standard deviation above the mean. So to calculate this with the formula, I'm going to do x. X is the actual score itself, 1300, minus the mean, 1100, divided by the standard deviation, which is 200. All right, and that's going to be 200 divided by 200, and there is that 1, a z-score of 1. And so what I would say if I had to interpret this is I would say that 1300 is 1 standard deviation above the mean. One standard deviation above the mean. All right, so if I want to deal with this 750 now. Now, if I look up at the top of the page when we did this top, okay, let me scroll up here. 750 would have been somewhere in between -1 and -2 z-score, somewhere between 700 and 200. So I know it's going to be somewhere between -1 and -2, somewhere in this range. -1 to -2, somewhere in here. So I'm going to calculate it. Z equals my actual score, 750. Minus the mean, 1100, divided by the standard deviation, 200. Put that in my calculator, I get -1.75, which does follow that it's somewhere in between -1 and -2. If I was going to interpret this, this is the number of standard deviations. So I would say 750 is, now I'm not going to use the negative sign here, 1.75 standard deviations. So the unit on a z-score is standard deviation. That's how many standard deviations it is, but we're going to say below the mean. Okay, so we deal with that negative. If something has a negative z-score, we know it is below average. We know it is below the mean. Okay, z-scores can help us compare some data values. So Ruben has taken 2 tests in his math class. So he has his first test and he has his second test. Okay, on the first test, he scored a 72. That's Ruben's actual score, so that's his X there, for which the mean was 65 and the standard deviation was 8. He received a 60 on the second test. That's his actual score. That's his actual observation, X, for which the mean was 45 and the standard deviation was 12. In comparison to the other students, did Ruben do better on the first test or the second test? All right, so when we're talking about in comparison to the other, obviously he did better on the 72 than he did the 60, if we're just talking about him. But how did he compare to the rest of the people taking this test? So we do know that he was above average in both of these, but the z-score will tell us how much above average. So I'm going to say z equals X, 72, minus the mean, 68, divided by the standard deviation of 8. This gives me a z-score of 0.875. Now, in terms of like what this looks like up here on the picture, that would be somewhere in that region up there. Okay. So it's, he's a little bit above average, 0.86, yeah, somewhere in here. And then for the second one here, z equals X minus the mean divided by the standard deviation, which was 12. And I wrote that very strangely. I'm not sure why. And that equals 1.25. Okay, so that's going to be right here. Okay, so which score did he do better on? Well, he did better on the second test. And the reason why is because he was farther above the class average. So he scored better on the second. He scored 1.25 standard deviations above the average student, whereas in the first test, he only scored 0.875 standard deviations above the average student. So he's closer to the edge of the curve on the top for the second test. He's farther above the average. He did better there. He's excelling. He is bringing himself more differentiation in that one than he is the other one. Stacy is in the same math class as Ruben. Stacy's z-score for the first test was negative 0.75. So Stacy is somewhere over here. What was Stacy's score on the first test? Now, I know that if her z-score is negative and she took the same test as Ruben with the average of 65, if her z-score is negative, that means her score should be somewhere below 65. All right, so just as a reminder, that z-score formula, z equals X minus the mean divided by the standard deviation. So her z-score is negative 0.75. Okay. Her mean is 65 and the standard deviation is 8. So I'm going to multiply by 8 and then I'm going to add the 65 over to the other side. And when I do that, I get X equals 59. So Stacy's score was a 59 on the first test. All right. So going back up here, the z-score tells me the number of standard deviations above the mean. Ultimately, what I want to be able to do is I want to answer questions about the percentage of scores for things that don't necessarily fit on that empirical rule set of rules. So what do you do with the 1.75s and the 0.86s and all that kind of stuff? So we have something called the standard normal curve. Okay, now there are lots and lots of normal curves. Your normal curves can have lots of different means and lots of different standard deviations. The standard normal curve, its x-axis is actually a z-axis. So it's always going to have a z on here. It has a mean of 0 and a standard deviation of 1. Okay, the mean z-score in the middle is 0 and 1 standard deviation, 2 standard deviation is just 1 distance there. Underneath this curve, it adds up to 100%. So the idea is that basically what this is it's like a very interestingly shaped pie chart. Okay, there's 100% underneath it. And so when we are talking about the probability of getting a certain value or the proportion of values, just like in a pie chart or in a segmented bar chart, we're looking at the proportion of area under that shape or inside those boundaries. So if I wanted to find the probability, so I've got this value A here. If I wanted to find the probability that Z is greater than A, or in other words, if I'm looking for like how much of the curve, how much of the data is greater than A, then I would take this area over here on the right. If I can figure out what proportion of the area of that 100% is under there, that would give me that answer. Similarly, if I want to find less than, I could find this area in the shaded region over here. And the cool thing about this is that all of these areas, this curve is modeled in your TI-Nspire, which means that if you have your TI-Nspire calculator, it knows not just the empirical rule, but it knows the area under the curve in every region you could possibly want, as long as you can tell it where to look. All right, so a little bit of a note here. If we're finding the area under a curve, that sure does sound like calculus, doesn't it? But we won't be doing any calculus because our calculator has it programmed into this for us. All right, so here are going to be your steps that you're going to do. You are going to draw, shade, and label your normal curve. Okay, we'll talk about this more later, but that means every single time you are going to draw the normal curve out, you're going to label your variable here. This is going to be a z. For this section, you're going to write normal, mean of 0, standard deviation of 1, and then you are going to shade it. You are going to find your boundary that you're interested in, and you're going to shade one side or the other. Then we're going to use something called the NormCdf command on our calculator to calculate the area. You're going to do this in just a regular scratch pad. Once you're in scratch pad, you're going to press menu and statistics. And you're going to go into a menu which is called distributions. The distribution is going to have the normal distribution that we're looking for in there. And we're going to pick number 2, which is this NormCdf. Okay, so I think this is 6 for statistics and 5 for distributions, and then 2 for the NormCdf command. Okay, and then I'm going to answer our question. All right, so find the areas under the standard normal curve for the following z intervals. All right, so I'm going to switch my pen here to blue. So the first question says, what is the probability or what proportion of the curve is less than z equals negative 1.22? So I'm going to come over here and I'm going to draw this picture. Okay, here's my normal curve. Okay, I'm going to put a z. It's z-score, so it has a mean of 0 and a standard deviation of 1. 0 is going to be in the middle. There's 0. So negative 1.22, that's going to be somewhere over here. I'm going to draw in that boundary. Negative 1.22 would be right there, somewhere. And it says less than. If I want the z-scores that are less than negative 1.22, that means I want the z-scores to the left. Okay, so I want all this area. So one of the things my calculator is going to want from me is it is going to want the mean and standard deviation, which I know are 0 and 1, no problem. And it's going to want where is the shaded region? What is the lower bound? What is the upper bound? So in this case, the lower bound is the very lowest this goes. Now, it goes forever and ever and ever over here. So the lower bound is actually negative infinity. And my upper bound of the shading is 1.22. All right, so I'm going to go to my calculator here, and I'm just going to use a regular, plain, old, ordinary spreadsheet. Sorry, a ordinary calculator page. I'm just going to do this in the scratch pad. So I'm going to press menu, statistics, distributions, and then there's several things that say normal here. I want number 2, NormCdf. CDF. And notice it says lower bound, negative infinity. Awesome. It already defaults there. So I want the upper bound. Okay. My upper bound. Oh, I've got some static going on my screen giving me some crazy wild stuff happening. Hold on. All right. Not even sure why that's happening. It's like no whammies, no whammies. Let me escape out of this, see if I can make it better. Menu, statistics, distributions. I want NormCdf number 2. Lower bound is negative infinity. That's great. And for the upper bound, I'm going to enter negative 1.22. The mean is 0, standard deviation is 1, and I hit enter. And I get fed back from this point, 1, 1, 1. All right, so here's what that means. That means that the proportion of the curve between those areas is 0.111, or in other words, that is the probability. We're looking at about an 11.1% chance of getting a number between negative infinity and negative 1.22 on this curve. Okay, so this NormCdf, what this actually is telling us, the CDF part is the cumulative density under the curve. It's going to actually tell us how much area is under the curve within that region. You put in the boundaries, it tells you the area. Okay, here's another one. It says z is greater than negative 2. All right, so I'm going to draw my curve. I'm going to write my z-score in. Since it's a z-score, it has a mean of 0 and a standard deviation of 1. Okay, and let's see. I want 0 in the middle, so negative 2 is going to be somewhere over here. Negative 2. And this says greater than negative 2. So greater than negative 2 means I want the area on the right side, greater than. So that means this time my lower bound is going to be negative 2, and my upper bound is actually going to be positive infinity. Okay. All right, so I'm going to go to my calculator. Okay, and I'm going to go Menu, Statistics, Distributions, NormCdf. On my lower bound this time, again, is negative 2. So negative 2. So I'm going to take out that negative infinity. I'm going to tab down, okay? And then positive infinity, upper bound, I need to put positive infinity. Well, positive infinity is a really big number, and there's lots of ways that you can access this. We can actually access an infinity button. I think it's down here in this little pi button, maybe. Is that where it is? Yeah, so infinity is actually hiding in there, and you can use that. But some of my older model calculators, some of those touchpads don't really like that infinity button really well. So instead, I've always gotten the habit of just putting in a massively huge number. So for infinity, I type in 10 to the 99th power, which is big enough to manage infinity because as far as z-scores go, 99.7 of them are between negative 3 and 3. So this puts us well out of that boundary. All right, I click enter and I get 0.977, 0.977. And again, I'm always trying to use at least 3 decimal places on these. So this is 0.977. That's the proportion of that curve that is between, or that is greater than negative 2. Okay. All right, what about the proportion between 1.2 and 2.25? So again, I'm going to draw the curve. You're always going to draw the curve. Always. You're always going to draw the curve. Okay, we're going to do normal, 0 and 1. Okay, I know that 0 is in the middle. That gives me 1.2 is going to be somewhere over here. Here's 1.2. And then 2.25 is going to be somewhere over to the right of that, 2.25. And we are interested in knowing what proportion of the curve is in between those two values. All right, so my lower bound is going to be 1.2 and my upper bound is going to be 2.25. So I'm going to go back to my calculator, Menu, Statistics, Distributions, number 2, NormCdf. On the lower end, I have 1.2. On the upper end, I have 2.25. And since these are z-scores, the mean is 0 and the standard deviation is 1. Right? This gives me 0.103, 0.103. So that means this is 0.103 right here. That is the proportion of the curve. About 10% of values have a z-score in a normally distributed population, somewhere between 1.2 and 2.25. All right, so if you're looking for the proportion of the curve that you get, which comes up to a probability, basically. We're saying, you know, there's like 10.3% of these, and there's 97.7% of these. 11.1% of these values are in this particular range, and our calculator is able to handle all that beautiful detail. All right. So let's look at a couple of examples here. Data from the article, The Osteological Paradox, Problems in Inferring Prehistoric Health from Skeletal Samples, suggests that a reasonable model for the heights of randomly selected 5-year-olds from a normal distribution with a mean of 100 centimeters and a standard deviation of 6 centimeters. And the first thing it says is sketch the curve for this information. So I'm going to sketch a curve. Here's my normal distribution. Okay, it says that we're measuring things in centimeters here. So instead of putting z, I'm going to put the unit, centimeters. I'm going to use the n for normal, and I'm going to put my values. 100 is the mean, and 6 is the standard deviation. All right, so I'm going to go ahead and label 100 right here in the middle. All right, so there's the sketch of my curve, and it says, what do we know here? Let's talk about Anna. Anna is a 5-year-old whose height is 94 centimeters. What does this mean? What is her z-score? All right, so 94 is going to be somewhere over here on this side, which tells me that she's going to be below average. So we're expecting that her height is going to be below the mean, so it should have a negative z-score. So I'm going to go z equals her actual value, 94, minus the mean, 100, divided by the standard deviation, 6. That is negative 6 divided by 6. That is negative 1. All right, so what does this mean? All right, so I'm just going to try to type in here. Okay, this means that Anna is, or Anna's height, I guess. Anna's height is 1 standard deviation, that's the unit, okay, below the mean. Anna's height is 1 standard deviation below the mean. That's what we know about her. The other thing that we could figure out here is we could figure out Anna's percentile. If I was interested in Anna's percentile, what percentile of height is she? Remember that the percentile is the percentage at or below. So I could actually, I know her z-score is -1. Like, what percentage of the curve is lower than that? I'm going to go ahead and figure that out. So as long as this is normally distributed, I should be menu, statistics, stat calculation, oh, sorry, wrong one, distributions, and NormCdf. If I go from -infinity up to -1, which is her z-score there, I get a number of about 1.158, so about 16%. Okay, so if there's about 16% on the left, what that tells me is that Anna is at the 16th percentile. That means that Anna is as tall or taller than 16% of 5-year-olds, and that she's actually shorter than 84% of 5-year-olds. All right, what about Bobby here? Bobby is a 5-year-old. He has a height of 111 centimeters. That's going to put him over here. He is going to be above average. So we would expect his z-score to be a positive number. Okay, so I'm going to take 111 minus 100 and divide by 6. That's going to be 11 divided by 6. That gives me 1.83. And you should, in general, try to use at least 2 decimal places for z-scores. All right, so what does that mean? So this means that Bobby's height, oh, goodness gracious, I can't type. Bobby's height is 1.83 standard deviations above the mean because it is positive. 1.83 standard deviations above the mean for him. All right, and again, we could figure out Bobby's percentile as well. Okay, how tall is he actually? What is that percentile? What percentage of area is there to the left? Okay, so I would take my calculator and I would do menu, statistics, distributions, NormCdf. How much is there from -infinity up to 1.83? And since this is normally distributed, we're talking about 97%. So Bobby is in the 97th percentile. Bobby's tall or taller than 97% of 5-year-old boys or 5-year-old kids. And then that means that there must be 3% who are taller than him. All right, so percentiles, again, are a value. The percentile is the particular value where that percentage of values are at or below. Okay, so in this case, I have a stem and leaf plot here, and I've actually counted ahead of time. There are 44 values in this data set. If I wanted to know at what percentile is the score 1610, right here, 1610, I would need to figure out what it was. So I'd make 1, 2, 3. I would count through and count how many numbers there are, and I would find that 1610 is actually the 25th number. Now remember, that's not the 25th percentile. It's just the 25th number. So it's actually the 25th number out of 44 numbers. That is 0.5, 6, 8, etc. So we would say this is at the 57th percentile. All right, so the idea is that 1610 is the 57th, I can't spell it, percentile. Oh, I just give up. Okay, it's at the 57th percentile. Okay. Which means that 57% of the values are at or below that, and 43% are higher. Percentile. Okay. All right, what score is at the 25th percentile? So if I want the 25th percentile, I want 25% of the values at or below. So 25% of 44 is 11. So if I take 11, I need to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. That's 13/5. That is 1,350. That is the 11th score out of 44 scores, putting it at the 25th percentile. Okay, so if I know the data, if I know the boundary, or I have the actual values, I can figure out the percentile. Like up here with Anna and Bobby, I knew the mean, I knew the standard deviation, so I could use that NormCdf command. Or if I'm looking at a chart like this, I can physically count and I can figure out the percentile. But sometimes it doesn't work that way. If you want to know what percentile it is and you don't necessarily have the boundaries, you may have to work backwards. So we have another command called inverse normal, and this is going to be just as easy to do as NormCdf. It's in the exact same place. The only difference is it's number 3 instead of number 2. Okay, is you can actually find the z-score with the specified percentage or proportion to the left. So your calculator only knows we're talking about to the left here. So what happens is when you're dealing with this value, instead of putting in boundaries and it feeding back a percentage to you, you put in the percentage and it feeds back the boundary. So it's called inverse normal because it's working backwards from what we did before. So for example, results of a recent exam were approximately normally distributed. Here they are, boop, normally distributed. What z-score is at the 90th percentile? So if this is z, I know that it's normally distributed with a mean of 0 and a standard deviation of 1. 90th percentile, so the mean here, 0, that's the 50th percentile. So the 90th percentile would be some value over here. I want to know what value has 90% of the curve to its left. Okay, so I can't use NormCdf because NormCdf's first question is, what's the lower bound? Okay, that's negative infinity. What's the upper bound? I have no idea. That's what I actually want to find. Okay, so instead, I'm going to use this inverse normal, which is going to be number 3. Okay, and I'm going to figure out the area to the left 90%. So I'm going to take my calculator here, and this time I'm going to go Menu, Statistics, and Distributions, but instead of picking NormCdf, I'm going to go down one more, inverse normal. It says area. It literally means what is the proportion of the curve to the left of the thing you're trying to find. So I'm going to type in 90%. I want something that has 90% to its left. Mean of 0, standard deviation of 1. And I end up with 1.28. 1.28. I'm going to go back. Okay, so that means, and that makes sense because remember this is z equals 0, so it would make sense for this to be a number bigger than 1 over here. So my z-score at the 90th percentile is 1.28. Okay, so you could use this for any percentile. What z-score is at the 25th percentile? You're just going to enter 0.25 to the left, or 50th percentile, that's 0.5 to the left. If you want the z-score at the 75th percentile, trying to find that third quartile value, you can put in 0.75 to the left. So any point in time, you can figure out any z-score that has any percentage to its left by using this inverse normal. Okay, once you have that, you could say if the mean and standard deviation were 85 points and 6 points respectively. So this is the actual mean and standard deviation of like x, of the z-score. Of the actual exam score. What actual exam score, what actual x value puts you at the 90th percentile? Okay, so there's two ways you can do this, but the easiest probably is to take your z-score formula. And just like we did with the test grade from earlier, we know that our z-score is 1.28. And we know that we're looking for the actual score, which has a mean of 85 and a standard deviation of 6. And if we go through and do our computation, multiply by 6, add 85, we're going to end up with a score of 92.68. Okay, so that would be our actual score, which makes sense that someone would have a high score if they're going to be, if the average was an 85, somebody who's in the 90th percentile is well above average. Okay, so I have another example. It says determining the statistical characteristics of vehicle emissions audit procedure suggests that the emissions of nitrogen oxides in parts per billion, change colors here, are major constituents of smog. It can be plausibly modeled using a normal distribution with a mean of 1.6 parts per billion and a standard deviation of 0.4 parts per billion. Let X denote the amount of pollutant emitted by a randomly selected vehicle. And suppose that the EPA wants to offer some sort of incentive to get the worst polluters off the road. All right, so at what percentile for emission level are the worst 20% of vehicles? So I'm just going to sketch this again. All right, so if this is parts per billion, not Z, but parts per billion, I know that I have a mean. It's approximately normally distributed. Mean is 1.6, and standard deviation is 0.4. Okay, so where are the worst polluters? The worst polluters would have a very high amount of parts per billion. In other words, they would be the one with the most pollution. So that puts 20% above whatever that worst polluter is. Whoever this guy is right there, that's the worst polluter. And there's 20% above that. Now, a percentile is the proportion at or below. So if there's 20% above, that means we're talking about the 80th percentile. Okay, we're looking at the 80% to the left because this adds up to 100%. Okay, what is the z-score for the emission at this percentile? Now, if I'm talking about a z-score, remember that means that my mean is 0 and my standard deviation is 1. And if I'm looking for the z-score at the 80th percentile, like what is that value? That means I want 80% to its left. All right, and since I don't know both boundaries, I'm looking for a boundary, I'm going to use my inverse normal command. So menu, statistics, distribution, number 3, inverse normal. I want 80% to the left. You tell me the z-score. Okay. And it comes up to 0.84, 0.84, right? And that makes sense. It's above 0 here. So the z-score is 0.84. So what does that mean? It means that the cutoff for the worst percentage of polluters is 0.84 standard deviations above the average polluter. Okay, now given the mean and standard deviation, estimate the actual emission level. So in other words, I want like X equals how many parts per billion. That marks the border for the worst 20% of vehicles. I want the actual number. So not with 0 and 1, but with 1.6 and 4. So we could do the same thing we did above. We could set up the z-score formula here. We know that the z-score is 0.84. And we know that the mean of the actual value is 1.6 and the standard deviation is 0.4. If you do this, this will definitely give you your 1.936, which is that boundary. You can solve for that problem. But your calculator can do this as well. I don't know if you've noticed, but as we've been plugging this in, we've been dealing with z-scores. So we've been leaving the mean as 0 and 1. But on each of these, NormCdf and inverse normal, okay, menu, statistics, distributions, inverse normal, you can change that. So if the area to the left is 0.8 and the mean is 1.6 with a standard deviation of 0.4, since this isn't 0 and 1, it's not going to give me the z-score value with 80% to the left. It's going to give me the actual x value with that to the left, which is 1.936 here. Okay, and we have a little bit of a difference because of rounding and whatnot. Okay, all right, so when we were talking about z-scores and normal distributions and whatnot, we're basically going to be crunching some things in our calculator. We're going to be sketching. We're going to be thinking about how the probabilities are under this curve. Okay, thank you very much, and that's the end.